Okay, so today I will explain the submission system. It might be a little bit confusing because the submission system is separate from Git and committing to GitLab, and also it has its own timeline. So we had deadlines for doing work. We commit the work to Git, and then suddenly we have to submit it into submission system, which means we have to like do a bit of a self-evaluation and put the URL into the system. And the reason why we have to do it is to make you reflect a little bit on your work, and also to organize our work, mine, and the TAs, such that we know who did what and what things and where things are. Because otherwise we have like 60 students, we have to go to the workspace and dig out of where the projects and tasks are and so on. And then you basically have to tell us, yeah, go to this URL and the task is there. So the submission system is like a specially designed system for students to submit their work, to submit assignments. In our course, we call it tasks. In PROG2005, in Christopher's course, he calls it assignments. And inside the system, we call it assignments. But it's basically like a piece of work that you submit. The submission has a form, and you have to fill it up. When you are submitting, there is a form. And usually there is this URL that you have to copy and paste. And it is the URL to your Git repository or to the project. You have to read the caption. Is it to the project, like HTTP page, or is it to the Git? When it asks for the Git, it means I can copy and paste it into terminal and say git clone and it will work, okay? So if it says project, then it means I can copy and paste it into a browser and open a page somewhere, right? So when it says Git, try to make it a Git, like copy and paste it from your project such that a person can go and say git clone and this URL and it will work. We often have some additional things for self-evaluation. The system asks you, do you have a README file, or have you done some tests, or did you run it with this or with that? And then it's either tick boxes or you have to type a little bit. So allocate a little bit of time, because the submission is not like 10 seconds thing. It may take like, a few minutes. Like you actually have to think a little bit. The first three, which we did, so if we go to the issue tracker, I announced that we already have some ready. We had those, why I am in the PROG 2005. Okay, so let's go to our course. Let's go to our course. And let's go to issues. So I announced initially the 246. 246 were work in the class. That was really easy, and the submission was quite straightforward. So that one was just to warm us up. And those people who did 2, 4, or 6, they could submit and try the system. Task 1 is actually quite complicated. So people who did task 1, now there was additional CSV file where you're supposed to test your implementation on, right? So that requires you to actually run what you've done on this new test file. And then when you are submitting, you have to enter some things. You have to enter what was your error, what was your count, and did you did the formatting correctly, and so on. So why are we asking all those questions? Well, we're asking it because then you can think a little bit of what you've done, what assumptions you've made, what decisions you've made for your implementation, and whether it works in those new conditions, right? So the form does not really violate from the specification, but it kind of exploits some holes. It exploits some things that you might have assumed or that you might have didn't thought of. And now when you're submitting, you have to think about it, right? It's sort of, it is a learning tool. It's for you, and if I was a student as well, it's for me to think what I've done and how I've done it, okay? So task 1 is a little bit complicated because it may take you about 20 minutes to actually submit this, okay? So you have to do some things, and then you have to copy and paste them into the form. As I said, it is mostly for you to learn. we have this discussion. So I'm sidetracking now. We have this discussion in the department at ED, at NTNU at large, how to work with AI and what it means to have a learning environment. And some teachers say we should not have grades. We should not really kind of assess you because that's not the main point. The main point is for you to learn. And the submission system forms mostly about you learning. But as you know, we have to rank you. Like we have to say, oh, those students were the best in the class and those were average. Society sort of expects us to do this. I don't like it personally. I feel it is really pointless. But we have to do it. So the submission system also is used for us to sort of assess the level of the level of achievement of the tasks and how you've done it. Will it impact your grade? Yes, it will impact your grade a little bit. But because we have a portfolio, you can always submit something and say, oh yeah, I've done task 01 to 50%. I haven't finished this, and that's okay. And then for the portfolio, you can do 100% and you can like catch up, right? So even though we have a deadline for the submission system, and even though you have to submit and say what you've done, you don't have to be bound by this for your grade because you can do more later, right? And then the heavy weight is from the portfolio, is from the final submission and what you finally did in the course. But there is a little bit of a premium for people being on time and for people doing things by the deadline, such that those people get a little bit of extra points, right? So if you're looking for an A or B grade, you should try to do all the tasks and everything, as we say, by the deadlines, such that you're sort of demonstrating a good progression and good timing. But you can still get C or B if you kind of catch up later for the portfolio, right? But don't expect to get an A if you do everything in the last week and say, yeah, this is my portfolio, I've done everything, but I didn't work for the whole semester, right? Then it will kind of not work. So the submission system, as I said, is mostly for you to reflect and mostly for you to learn. We have an extra thing. That's why, I mean, if it was just the submission, we would use Blackboard or something else, but we have an extra thing in the submission system, which is ability for other students to see your submission and to have a review. And this is called peer review. And this is not done for all the tasks, but it is done for some tasks, which means after we have a deadline for submission, there will be like another deadline for reviews. So you go back to that assignment, you will be given like 2 or 3, or like it depends how it is configured, other people's submissions. And then you will have your other form where you have to say, oh yeah, like for example, what is the quality of testing, or what is the code quality, or what is the quality of the README file, or does the project compile, or things like that. So you will have to do a little bit of peer review of somebody else's work. And that means seeing their submission and also seeing their code. That's why we have to make the code available for internal, such that other students can see your code and can give you feedback. So it is sort of like submission is one thing. Then there is a peer review, not for all the submissions, but for some. And then after peer review, the review is being reviewed by the person who got the review again, right? So if I'm a student, I submitted, let's say we're talking about the accountant task. So I've done the accountant task, I submitted my stuff. Then I will see somebody else's work and I will sort of assess how well or what strong and what weak points are there. And then the person for whom I'm assessing will assess the feedback. So the person will say, oh yeah, the feedback was useful, or the feedback was not useful, and so on. So it's like a 3-step process for some of the tasks. It takes a bit of time. That's why we have those kind of deadlines being a bit stretched. And that's why we sort of not rushing it with the deadlines which we have for the work. So you have your own work to do the tasks, and they become harder now. There is more to do. So the deadlines are a little bit more flexible. So instead of 1 week, we have usually 2 weeks. And if you tell me, yeah, that's not enough, we have other courses and we are kind of heavy loaded, we can make the deadlines even more flexible, right? So like you have to tell me, but I'm making some of the deadlines already more flexible. And I didn't posted the obliques yet because the obliques also will have like a mini quiz where you have to enter some stuff. So it sort of is a feedback to you that you've done the obligatory work, but did you really learn? So there will be some sort of a quiz questions for you to assess, okay, I sort of learned this, I got it. Or it's like, oh no, I have to spend a little bit more time on faults because I sort of still don't get it. So the forms are a little bit more complicated, and again, they will take a little bit more time, and they have not been released yet. So I'm kind of fine-tuning it and making sure that we have it done well. And then I will announce it here that you have those new forms for like task 5, I think, is oblique, and 7, I think, is oblique. No, 7 was the snake. Maybe 3 was oblique. So some of the obliques are not here yet. So I will kind of post it as we go and make enough time for you to submit it. But you know, there are deadlines and you should keep the deadlines, because if you don't, then the whole thing kind of collapses. So if you're struggling with time, if you say, oh yeah, there is a little bit too much, then tell me early so I can kind of extend the deadlines. It's a little bit tricky with the submission system. Like once the deadline is set, it affects the deadlines for the reviews, and this deadline affects the deadlines for the feedback for the reviewers. So there is kind of a dependency, right? So I need to know earlier that you're struggling and we need more time. Is that clear? Right, so I hope it is clear. It is the same system in the cloud. So Christopher is doing the same, using the same system, but he has less things. He will only have 3 assignments. And for all 3 assignments, he is using peer review and feedback. We are not doing peer review and feedback for everything because that would be an overkill. Like we have too many things, but you will have to submit all the work that you've done. So we will have submission tasks for all the tasks that we have in the course, but they are not ready yet. So as I said, I'm kind of working on it and fine-tuning it. All right, so this is the submission system. There is a wiki page for how to use it. The system is accessible via VPN if you want to use it from home. So it's kind of the same as in the cloud. I think Christopher told you already. There is a URL. So for each course, there is a special hash. And for cloud, you will have a different hash. And then for our course, there is a different hash. If you click on the hash, if you click on this link and let to log in via GitLab, everything is automatic. You don't have to be approved and you get into the system like out of the box. If you say, I want to have email password thing, then Christopher has to approve you. So you get into a waiting list and then he has to approve you and then you get into a course. But once you have the login sorted, and I encourage you to use the GitLab login, it works seamlessly. Then it is kind of fast. The system may be buggy, so there might be things that don't work. One of the biggest bugs which we had before was that if you open a submission form and you spend time doing the submission, it times out, and then it does not store what you entered. And students get really frustrated, like I would as well, if I was filling in and then suddenly everything is wiped and you have to redo it. So right now we have autosave. It saves your form as you entering it such that you can come back to the form, but you can always press submit and you can always come back and change it until the deadline, right? So it's a little bit like with those old systems, which autosave was a little bit wonky. Here the autosave works, but to be on the safe side, you have to make sure that you click submit occasionally. I got caught last week. So from home, I have to use VPN. And on Mac, if I don't touch my laptop for about 5 minutes, it kind of goes into a sleep mode and the VPN client disconnects. So I actually lose internet. So I was working on the submission form for task 1. And then my wife called me. I went to fix something for her. I came back and said, shit, I didn't press submit. I pressed submit, but the VPN was disconnected. So it was like, oh yeah, you're not connected to internet. So the form get wiped. It's like, oh no. So like when you press submit, make sure you are connected to internet, because if you're not, then like, bad things will happen. So I lost about 20 minutes of entering the form, and it's like, shit, I have to redo it. Super annoying, but it was my fault. I didn't notice. And there is no autosave for preparing the forms. For entering the forms, there is autosave, but for preparing the form, for admins, we don't have autosave at the moment. So yeah, so just a warning. If you find something not working with the system, just tell Christopher or me, or make an issue in the issue tracker. And of course, we will try to fix it as soon as possible. All right, so other announcements. For the previous task, which was task number 8, I have entered, so what we were doing word count, like using the coding agents and trying to see how well they work and how quickly can we do something relatively simple. And I posted my trace. So this, in this folder, I have git commits. Every time I was doing a prompt and I was committing what the agent was generating. And then there is a file called something prompts. And it kind of keeps track of what I was doing and like what the coding agent was doing. So I told it to generate certain files before it started and so on. So you can see the process. Is that the best process? I don't know. I don't think so. As in most programming things, it's a social activity. So we learning what is the best way for communicating with other humans. And now we also learning what is the best way to communicate between us and the agents. And we have to learn. So I'm learning, same as you. And this is just my process. It may give you some hints. It may help you with your process, but you have to think how to make your work better, okay? I probably told you that before. I had a lecturer when I was a student, and he said something that kind of stick with me, is that our job, like the computer scientist or programmer's job, is to sit and observe the progress bar. And you have to make the system in such a way that you have a progress bar and you can sit and wait. So it's a very philosophical approach to computer science and to programming, because it means automation is all we do. We trying to make computer do work that we can just sit and wait. But preparing it, like making all these tasks and everything such that we can sit and wait, is our job. So our job is to organize things and automate things in such a way that there is not much we need to do. It's just sit and wait for the progress bar, right? So as I said, the process is kind of described here. You can have a look, and we will come back to this next week. We will do a little bit more work with agents, and you will have a little bit more experience, because the task for today in the class and the task and the homework is also with the use of AI. All right, so this is that. Any questions for task 8? Task 9, I will commit when we have a break. So the task 9 is for us to do today in the class. And task 10 is the Punto game. So Punto is a kind of a board game. It's an abstract game. It's a little bit similar to Domino, but you are given a set of cards. So that's how it looks like. You can either play 2 players, 3 players, or 4 players. I have a friend who play with himself, but that is a bit odd. So every player gets a color, and there are cards from 1 to 9, and there are twice as many cards. So there are 2 1s, 2 2s, 2 3s, and so on, right? So you have the deck of cards, you shuffle it, so it's random. and then you put it on the table, and then in a round robin fashion, a player takes a card, sees the number, and then places it on the table. And you can place it on the table adjacent to a card which is already there. Or if your number is bigger than the card which is already there, you can put it on top, covering the other card. And the goal is for 3 or 4 players to have diagonal or line, horizontal or vertical, 4 of your color, right? So you're trying to organize the board in such a way that you have 4 in a row or 4 diagonal. If you're playing 2 players, you have to get 5. And with 2 players, each player gets 2 colors. So one player, let's say, play with red and blue, and one player plays with green and yellow or orange. And then you're trying to organize 5 in a row. So it's sort of like tic-tac-toe and a little bit like domino, but like a bit combination of both of those games. Why I'm talking about it? Because we want to implement this game in Haskell and play with a computer. So with Snake, we were just playing with another player or with ourselves. It was a little bit more tick-based game. So we have like some sort of update loop. We have to plan what happens every tick. Here, it's a turn-based game. So each player makes a turn and then the other player makes a turn. So we want to represent the game as a ADTs in Haskell and make the game playable across people, but also to play with a computer. And to play with the computer, we have to know what legal moves are and what is sort of a strategy to win. And to get a feel of what can be a strategy to win, you have to play it. So you have to play the game a few times to get a feel of what you need to do to maximize your chances of winning. It is a chance-based game because the decks are shuffled, so you can only making local decisions based on the card that you get. So you cannot plan. It's not like chess where you can plan many moves ahead, because every move there is an element of chance and the board changes, right? So when you're placing the cards on the board, you cannot build the board bigger because it will be kind of like a grid. So you're placing the cards like adjacent to one another, but the grid cannot be bigger than 6 by 6. So the maximum dimension this way and this way is 6 cards, okay? So if we have some cards already there, you can try it out. So you can organize. And you can try and play it. In task 10, there is a short video about the game. So if you go here, there is a short video about the game, like 2 minutes, and there is the instructions of how to play the game. It's just 1-page PDF. So it is like you can check it out, and then we can have a bit of fun and play it. Any questions about that? So for this task, the basic thing is to implement the game and such that people can play it with other people, right? So that's the foundation. Once you have that 2, 3, or 4 people can play, you don't have to do 2, 3, and 4. 3 is like a special case because you have 4 colors but only 3 people. So there is extra rule that people get half of the other color and blah, blah, blah. It kind of complicates life. So let's focus on 2 players or 4 players, because then it's like simple, okay? So not for 3 players. So once you have it sorted, then you would like to play with the computer. So let's say 2-player game, you against the computer, or a 4-player game where you are against 3 other players, but all 3 are computer players, right? So then there are 2 options. Oh, there are many options, but they are kind of fundamentally 2 options. One option is that you come up with some heuristic, you come up with some rules, and you make the computer follow those rules, right? So it's called heuristics. and you have to come up with them. Like you have to design them, right? So that's the normal way of doing stuff. A more fun way, and because you have a cloud course, is to send the board to LLM and say, what would you do? Like, where would you place the card, giving the board and the card you have to place? And LLM tells you, and then you play it, right? So you don't coming up with any heuristic. You're just saying, let's ask LLM to play with me, and then I will kind of make a call to LLM, and then I will do the move, okay? To do this, we have to have a local LLM such that you can actually interrogate it. And I'm trying to set it up. So this is not a requirement for now. We may or may not do this, but it would be quite fun because you're just making, like, you have to represent the state of the board in some way, prompt it to LLM, and then send it via REST API saying, yeah, this is the state, like with the prompt, and then give me the move. And then you will just play the move. And that would make the game really fun because you would actually could test different LLMs and play against different LLMs, right? It would require a little bit of JSON parsing and a little bit of text processing. But we should not do that with the public LLMs. I mean, we could, but we should not. We should have a local one. And I'm kind of trying to work it out. So I will update this task if we have a working server where you can kind of interrogate a LLM yourself. And then for those of you who want to try it out, and I'm like keen to try it out with LLM, so we can do it, but it's not a requirement. The only requirement is to make it against humans, and then if you can make it like some heuristics saying, okay, if I have a card and I can put it on top of an existing card, then let's do it. If I can expand the card limiting, because you have to like predict one move ahead and see if in the next move a player can win, because it's sort of like tic-tac-toe, like you're trying to block other players finishing the game if they can, such that you kind of usually play defensively. Like you're playing not to win, you're playing not to lose, right? So let's see how it goes. It is a little bit more about organizing and about organizing data structures and thinking about the game rather than coding, because we're using AI for coding. We sort of focusing more on those extra things, right? So the task here is not exclusively on coding. It's actually more about how to organize your game such that you can do those extra things with it, right? Okay, so this is task 10. And task 9, as I said, I will release in the break. And it is a bit of a strange task because you will not do any coding. You will read code, and then you have to think about it, right? So instead of you thinking about the problem and coding it, you will see the code, you know what it does, you will kind of try to identify what's wrong with the code and how to improve it, and why one way of doing things is better than the other way. Noticeably, it's a little bit beyond the level that we are currently with Haskell, right? So the code that you will be looking at has constructs which go a little bit beyond of what we already reached with the other tasks in Haskell. But it's the same with Snake. Like if you were doing Snake, we were going a little bit above like what we covered in the material. It's okay if you don't understand everything in the code. Like, so there are certain things, especially about containers and about monads, how we manage state in Haskell, that feel a little bit counterintuitive, let's say. And there are two ways of learning it. You can learn it like ground up. You sort of really understand how monads work, and then you say, oh, aha, you have this aha moment, and then you can use it. Or you're using something that you don't quite understand how actually it works, but you know how to use it, and then the aha moment comes later, right? And in Haskell, to be honest, a lot of those aha moments come actually later. Like it's so hard to kind of understand something before you use it. So it's easier to use something without fully understanding it, and then you will kind of understand it more and more as you use it. So monad transformers and managing state using containers in Haskell is one of those things that is not that hard to use. Like in the code, it's like, okay, yeah, I get it. Like I can use it this way. But how it actually works, like if I ask you now implement it, like make me like from the normal functions, make those functions, then it's super hard because you have to think a lot about certain concepts and it becomes kind of a little bit tricky. So as I said, task 9 is you will read code which may go a little bit beyond your level, which is fine. Ignore the bits that you don't fully understand, take note, and then maybe make an issue in the issue tracker saying, oh yeah, well, how does that work? Why we doing it this way? Haskell is also a little bit interesting because it has a lot of syntax decorators. Like everything is a function, but it has those extra symbols which make certain functions like easily to use. And it feels a little bit awkward. So you just need to practice a little bit. Yeah. Anyway, I hope it will be quite fun. And the task which we're doing today, task 9 in the class, actually goes for 1 extra week. So the deadline is not the end of the class. The deadline is actually next week. So you have more time to fiddle with it and to think about it and to submit it later. This one, I think, is 2 weeks. If it is not enough, you can tell me and we can make it longer. If you get collision between this course and other courses with deadlines for assignment, for example, for cloud, tell me, and then I will kind of update my deadlines, right? So I will make it more flexible. All right, any questions? If not, let's perhaps let's have a break and let's play some Punto for like 15 minutes. And then I will push the task as well. And then I have a lecture. So we have I hope about a 1 hour lecture before we can dive into the snake. All right, so let's have a break. And once the cards are ready, we can play some Punto. All right. All right, let's talk a little bit about Haskell. So first, let's go and talk about a typical use case where we have to yeah, there was some programming activities here. A simple activity where we have to do 4 things. See the pen. So I will wave my hands. So we basically have to get some input, either from a user or from JSON or from somewhere. We have to parse it and extract an email. And then the email might be broken. And that the step of parsing it can have an error as well. And then once we have the email, we have to say, is it the correct email? Does it have the sign, does it have like a host? Does it have the legal character? So we have to validate the email. And then we have to send the notification to that email. And then if all those 4 steps worked, we say, yeah, it worked. And if one of the steps failed, we have to say what went wrong. Like, was the input wrong? We couldn't get the input. Was the parsing, getting the email from the input wrong? Was the email kind of malformed? Was the sending of the notification failing? And we have like 4 things to do. 4 things can go wrong. And then at the end, if everything worked okay, we are done, right? A very, very common pattern that we have to do some things in sequence. And during that sequence, some things may go wrong, right? So in Go, how we do it in Go? In Go, we set our 4 steps, and each step can succeed or can have an error. So if we're getting the input, we're saying, okay, well, let's say the input is from the network. We're getting the input from a REST call, right? And then we're getting JSON back. So we're getting some form of JSON back. And one aspect of that JSON is email, right? So this is like a placeholder for the real implementation. It simulates how our method would look like. And the important thing is that we can return what we got, or there is an error, right? And then parsing the input and getting the email, we passing this JSON into this method, and it extracts the email. Again, we faking it here, but normally we would be like processing this JSON and getting the email out of the JSON, right? So again, things can succeed and we get the email, or things can go wrong and we get an error. And then we have to validate the email, that the email is correct. And then we either return an error, and in this case, we return an error because example.com is not a valid email, right? So we have an error because this is a host. It lacks the name ampersand sign for email address, right? So we say, no, it's an invalid email, right? So in this case, we're returning an error. But if everything went okay, we would return the email here with error being nil. And then we are sending notification. So we're getting the email, which we know is validated, is correct. We're sending it. And then in this case, the notification is correct. It says, yeah, it was sent. There was no error, right? And there is some sort of a string here. We could have just error. We don't need to return this string, but keeping the signatures of all those methods the same allows us to do certain things in a consistent way. It allows us to chain the functions because they have the same input and output, right? So even though we technically don't need a string here, for this type of processing, it is convenient to sort of organize our code in such a way that it is consistent across all the 4 calls. Does it look good, like to you in Golang? No magic here, right? It's just a standard Golang returning something plus error, right? So then our processor combines all those behaviors, right? So we have a process method, which is supposed to do 4 steps and either return an error or say everything went fine, right? So now the question is, can you do it in a single line in Golang? Can you combine 4 of those behaviors in a single line in Golang? So yes, it is not nice not to have the pen, but let's cheat. So let me open terminal. So if I open a terminal, so there is a kind of a typical pattern. Um, okay, so if we have a normal imperative code, we usually do something like A equals and F1, we calling something, and then B equals F2, and it gets A as a parameter. And let's say we have C equals F3, and we pass B as a parameter, right? We've used up 3 lines of code. We could do it in a single line by saying F3 takes what F2 produces, and F2 takes what F1 produces, and we sort of chained it in such a way that we get all those 3 calls in a single line. We normally in Golang and in like imperative programs, we don't do that because it is a little bit less readable than doing this. But this manipulates the state explicitly. It kind of creates those variables. This one does not create any variables. It's kind of implicit, right? And in functional style, we often do that. So in Haskell, we would say, we would basically say this. We would say this, right? Let's say, okay, do F1 first, whatever that returns, pass it here, whatever that returns, pass it here. And then we have a single function. This is using dot notation, which means we don't have a parameter passed to F1. And in fact, F1 currently does not take any parameter. But if it did, it would be sort of like, because this is like a single function now, which takes whatever F1 takes, right? But in imperative programming, we usually do this. The question is, we can turn this into one line. But the question is, can we turn those 4 calls into one line? So one more person to vote. The answer is no. In Golang, we can't combine it in such a way into a single line. Why? Because the processor returns an error and it needs to combine those 4 calls, and we cannot pass, we cannot pass, you see, if we call F1, it returns something useful and an error. And we cannot combine like parse input and get email, and we cannot call get input here because get input not only returns a string that we want, but it also potentially returns an error. And that's why we in Golang, we cannot say parse input and get email, open brace, get input here, right? We have to do this if statement. It is by design, it is designed to have those if statements, because we have to deconstruct the email and the error separately, right? We have to deal with the email and with the error, and we cannot say, yeah, like pass it here if the email will be passed to the parse input and get email. So parse input and get email expects a string, it expects an email. But this function, the get input, returns 2 things. So it does not compose, right? So composability in this case is broken. Like we cannot compose it together, and we cannot do it in one line. We have to split it into this. And this is by design. And this is one of the most hated features of Golang, right? The composability is broken. We cannot compose. So we feel handicapped as programmers. We feel forced to doing like extra work that is not necessary, right? It feels wrong. Like for people who know other programming languages, that feels wrong. All right, so let's see how Rust does it, okay? So in Rust, it's similar. we have the same four functions. They can return they can return as a value or an error. It's the same principle, right? But we have a combined type. We have a combined type called result, which means all those functions deal with the sort of value and error in a consistent way. I mean, Golang also deals with it in a consistent way, but there is no type which says value and error. It's like a made up tuple, but it's not even a real tuple. Here it is a real type. And because it is a real type, we have this procedural or like imperative way of doing one thing, getting a value, doing a second thing, getting a value, doing a third thing, getting a value, and then doing the final notification. And you can see there is no if statements here, right? Magic, like where the if statements go, they are replaced with this question mark. So this question mark at the end says, okay, this call can fail with an error. And if it does, return the error to the caller, return the error to the function we are in. If that function succeeds, get the value out of it, right? It's fine. So now the question is, can we compose it into a single line? Can we compose things into a single line in Rust? Yes, we can. Yes, we can. Exactly. So now our call sort of looks like this. Where is my cursor? So we say F1 can return a value, or it can shortcut to the caller. So if we put a question mark here, it means if F1 succeeds, it will return a value, which can be passed to F2. If it fails, it will shortcut to the caller. So it will just return that error to the caller, which is great. So now F2 is the same, and F3 is the same, right? And we can do this in a single line of code because we have this question mark decorator. And this type of question mark decorator was argued and like requested from Golang since the beginning. And it is not likely to happen because the designers of Golang, they think those if statements are good. Like we should do those if statements. So yes, we can do it in one line. So it is the sort of a more imperative way of getting the inputs. We can do it in one line. So process notification, validate email, parse input and get email, get input, and then we have those question marks, right? So technically, yes, we can do it in one line. It can be done. It kind of looks ugly. So this, like, we don't write code like this because it's less readable. It is a little bit ugly looking. We basically write code like this, but we know it can be written in a single line. And also we know it shortcuts to the error here. We don't deal with the repeatable, bullshit looking if statements in Golang, right? It is like it feels just redundant. It feels wrong. Like why have I typed this? The logic is exactly the same here, and I don't have to type anything. I just put this nice question mark, right? And then it works. It works exactly the same as in Golang. It's just so much nicer to deal with, right? So Haskell, of course, we have, again, those four functions. They return either a value or an error. And in our case, the error is just a string, but we are using the either type. We have a value or the error. Actually, the error is on the left. So we have either an error on the left or a value on the right. And here we're returning the right side. Here we are checking if there is correct email or not. This is a bit like messed up. The email here is example.com, which is not correct. So there is a bug here. Sorry for this. Oh no, that is correct. So it returns the email out of the JSON, and then it says the email is wrong. It returns left because the example.com is not a valid email, right? So same as with the other examples, it returns the error. And then the notification kind of sends the notification. And yes, normally we can combine it with the bind operator in Haskell in a single line of code. So one line, yes, it is one line. We're getting input, we're parsing the input and getting the email, we're validating the email, and then we process notification, right? As you can see, the sequence, if we use the bind operator, is kind of actually readable from left to right. We don't get any intermediate variables, and we get this sort of a passing, like what is the output of this guy to here, what is the output of this guy to here, and so on. And then at any point, if one of them goes left, if one of them shortcuts to an error, it will just return the left error, right? So it kind of works the same way as with the question mark, but we don't have to deal with the variables, and we read it from left to right. Remember, like in okay, I have it here. In case of Rust, we were reading it like outside in. We kind of have to start inside and read it like from right to left to get the logic, right? In Haskell, we kind of read it left to right. So it is super nice. It is one-liner. This is inspiration of why Rust has the question mark and why Rust works the way it works. And in Rust, if you do it in an imperative way, not in the one-liner way, it is very nice. Like it is like, get input, do this, do this, do this. If there is an error at any of the steps, we will shortcut. And then if there was no error, it will work out fine. So this is kind of an important, like we usually don't write it as one line in Haskell neither. We kind of write it like this, like do this, do this, do this, do this, right? It's more readable and it's a bit easier to visually parse. So in functional programming, that's baked in. It's always like this. And we always have this sort of a happy path and unhappy path, and the unhappy path shortcuts. It sort of makes programming of happy and unhappy path easy. And if you watched, it's called railway-oriented programming, kind of a funny name for talking about functions, functional composition, and plugging things together such that we get a nice composable infrastructure or architecture, right? So in our case, we have some input, and the input can either fail or succeed. Then we have some parsing, which can either give us the email or fail. Then we have the validation, which can either give us an email or fail, or we sending the notification that it either finishes correctly, or we have some sort of error along the way, along the pathway, right? So if you sort of conceptually think about it, it's like nice progression of different activities, and each of the progression can shortcut to an error line and give us the error into the error handler, or we are successfully progressing to the happy ending here, right? Super nice, super easy, super convenient. This is another example where we have an exception, like we have composed our processing into this sort of railway-oriented programming. We're getting some sort of input validation. So the user gives us an input. We validate it. We can go into the unhappy path if the input is broken, or stay on the happy path. We're getting the user from the input. Then we're doing some database request. The database request is doing I/O and it can fail. Like our network may be down or something can be broken, and it's an unusual situation. So we don't want from updating DB to go to the unhappy path. We have to treat it as a special case, as an exception. It's not the unhappy path that we have to deal with, it's an exception that we cannot deal with. Like If the database is not there, there is nothing we can do. So it's an exceptional situation, right? The unhappy path is with stuff that we can do something with. So let's say the user gave us the wrong thing, validation failed, and we say, oh, look, your email is malformed or your input is malformed, to do it again, right? So we can somehow deal with the unhappy path. With the exceptional situation, we can't. So we have a little bit different behavior here. Then sending the email can fail, and we can tell the user, okay, we cannot send the notification. Please retry or please do something else. So unhappy path is usually for the error handler to deal with. The exceptions are for us to say it's unrecoverable. Like there is something like really broken. We have to deal it in a special case. All right. Have you watched the railway-oriented programming lecture? Who is Scott? He is a professional programmer who is also doing online lectures. So he is actually an F# developer who promotes and talks about object-oriented functional programming, and he makes some tutorials and lectures online. And I sort of, yeah, I like his style. All right. So those of you who watched it, did you like it? Did you learn something? Was it useful? Yeah, looks good. So if we learn something new from a tutorial or lecture, that's a win. Great. So now we have to dive a little bit into theory. The theory is a little bit boring, and the theory is not strictly needed for you to become a good programmers. I had a question last year, why do we need to learn about category theory? And normally you don't. Normally, if you're developing applications and if you're building end user things, you don't. But if you're building something more complicated, if you're building a compiler, or if you're building a framework, if you're building like a new web framework, you have some ideas of how people should be programming on the web, and you're building a new web framework, then knowing foundations of category theory helps you to organize your concepts and to organize your composability of your framework in such a way that it's nicer and you have a little bit more tools. So we don't stress it in the course. We just like touch the foundations. But if you really want to dive deeper, you will learn a little bit of algebra and a little bit of math and category theory, which will help you to sort of organize your thinking and organize your structures of the framework that you're working on in such a way that it's a little bit more designed, not ad hoc. It feels more designed, okay? So a little bit of theory. Binary function takes 2 arguments. Unary function takes 1 argument. Super simple stuff, okay? So a quiz. Oh man, 18 questions. Who designed this one? We will be kind of running out of time, I guess. Okay, let's go. No time to lose. Plus. Is it unary, binary, or ternary? Super easy. Yes, it's binary. It takes 2 arguments. All right. Question 2. Plus plus. Haskell. Concatenate. Unary, binary, or ternary. Obviously, ternary takes 3 arguments. Unary, 1 argument, binary, 2 arguments. Yes, it's binary. It takes left-hand side and right-hand side. It's a binary operator. Binary function. Okay. So plus was easy, plus plus not so easy anymore, or people misclick. Multiply by 100. What is this one? It's a little bit tricky question because you may get confused with multiply. So multiply by 100 is a unary function. It takes just 1 argument, which we have to multiply by 100. So unary, perfect. Yeah, we're doing well. 4 questions already done. So, wow, what is this one? What the hell? This one deserves a look into. So let's quit this. And go to our GHCI friend. So if we ask, okay, tell me about this function, what is it? Whoa, 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 it has a lot to say. So can I scroll? Yeah, I can scroll. All right, so it says, okay, it's a tuple 3, which has 3 things, and given the function takes 3 arguments. Basically, what it does, if I call it, so if I call this function with Mariusz 1 and true, it will create a tuple which has 3 things, right? So let's do a single tuple which has 2 things first. So if I call this function, it creates a tuple with Mariusz and 1, right? But if I do one extra thing, it creates a tuple with 3 things in it, right? So in other words, this function is ternary because it takes 3 parameters. Nice. All right. We have some people doing really well, and everyone is doing pretty well. All right. So identity element. So if I have an operation and I use this operation on an identity element, I get what I put in. So the identity element does not change the operation. It sort of introduces nothing. I can do something, but it sort of feels like doing NOP because what I got initially is what I get at the end, right? So if I have X and I do some operation with the identity element, I will get X at the end anyway. So it doesn't matter, right? It kind of feels useless, okay? It feels like, why would you do something like this and get X? But again, if you abstractly think about it, if we have a lot of things to do and to transform into a lot of other things, and some of them not supposed to get transformed, we can throw in the identity element and we uniformly doing the transformation and we don't have any special cases. We don't have any if statements. We don't have any we don't have to deal with it. It sort of is happening on the fly, right? So in a lot of cases, when we're composing something abstractly, we want to do this. We have to reuse this property and throw in the identity element such that it does not change for things that not supposed to get transformed, that it does not anything, right? So anyway, one example is plus with 0, okay? Plus is the operation. It has to be binary, and 0 is the identity element, which like does not transform it to anything, right? I can always add 0 to stuff and I get stuff. It's the same stuff which I put in. So give me other examples. Give me other examples of operand of some binary operation, and what is the identity element for that operation? Okay, what could that be? Perfect. Multiply with 1. Yeah. What else? Subtract with 0. Perfect. What else? Divide with 1. Perfect. You get the feel, right? So now you have to think a little bit more abstractly. Like, okay, what else can I do using functions from Haskell, for example, that have an identity element? Can you come up with something? Yeah, concat with empty list. Perfect. That's very nice. So the exercise is to kind of think more in those abstract structures, like concatenation and an empty list is like, gives us the same thing. All right. Next one, associative binary operation. So if we have a binary operation and we have x with y and then with z, we can do y with z first and then x with the result of this, and it will be the same. It does not change anything, right? So I can do x and y first and then z, or I can do y and z first and then x with the result of this, and it will not change anything, right? You obviously like immediately can see why this is useful when we have sequence of operations to do in programming, right? If I know I have 3 things to do, and it doesn't matter if I do this, then this, then this, I can reorganize it in a way that is more convenient for me, for the compiler or for the memory management or for the threads do stuff in different order, right? So if I know that this is exactly the same as this, I can do y with z and then do x on the result. So if I have this, but I have already calculated y and z, then instead of doing x with y, because I already have this, I can say, no, it's exactly the same, so I will do this transformation instead. And when you have your source code, your program says, do this, do this, do this, do this, but we know that the certain operations are associative. We can reorder in which sequence we're doing stuff. And the modern compilers are doing that. The modern compilers are looking at the sequence of your operations. They check what operations are you doing. Is the operation associative? And if it is, it will reorder it for the benefit of memory utilization, for I/O, like for asking about something. If I already have Y and Z in registers, I will do that first and then we'll do the other one because I have to fetch Y from memory, right? So there are certain transformations which happen because of this. So associative binary operation, again, it's very simple. You can think of the arithmetic operations that have this property. The exercise is to memorize it by simple, plus, minus, multiply, divide kind of things. They will stick in your head that it is associative. But then when you're programming and you're building stuff, you're doing operations as well. And you have to think, okay, is my function associative? Does it matter in which order I do stuff, right? Yeah. So multiplication is associative. Concatenation is associative. Plus is associative. Yeah, very nice. You're getting the idea. Perfect. So now we got to the very foundational concept. First concept is if we have, I cannot write here. If we have a binary operation and we have set which this binary operation works on, we have what's called semigroup. So a semigroup is basically a binary operation with the things that this binary operation work with. So for example, if you say integers with plus, it's a semigroup, okay? Like if you say positive integers without zero and plus, that's a semigroup. If you say integers with plus, it's a monoid because you throw in the identity element. So if the identity element is there, it's not only a semigroup, it's a monoid, okay? Again, a little bit abstractly, why it is important, like why we talk about it, because in Haskell, it's there. So you can ask about semigroup, and you can see which operations are actually examples of semigroups. And for example, ordering, for example, what other instance you have? Yeah, you have tuples. So tuples, like two tuple or three tuple or four tuples are semigroups. Either is also a semigroup. So, and then you can ask about monoids. And then it kind of tells you which operations and what is in Haskell, which is a monoid, which is they have binary operations, but they also have this identity element. So knowing those terms helps you, because sometimes when you ask Haskell, okay, what is this function? And it tells you, oh yeah, it is doing that, and it belongs to semigroup, you will know I can compose it in certain way. Like it has this associative binary operation, so I can compose it in any order, right? Which means I can do stuff in parallel, right? Because let's say you have to do certain transformations, and you know the transformation is a semigroup or a monoid, then the order doesn't matter, because you can do it from the right side or from the left side and so on. So you can say, do all of it in parallel. I don't care the order, it will be kind of okay. It is useful, but you have to sort of dive a little bit into it. All right, so then another one is a commutative binary operation, and it means I can, instead of doing x with y, I can do y with x, and it will be the same, okay? So commutative property, again, give me examples. Again, those are pretty simple. The trick here is to kind of know which ones are not commutative, right? So which one of those operations are associative and binary? Can you do multi-choice, multi-select? No, damn it. So yes, addition is and multiplication is. Subtraction is not, because yeah, subtraction should be as well. Division is not, because it depends, like whether you're doing the other side first. So that could be an error here. And this one is not, because it's a unary operator, right? So that one takes one argument. So here we're asking which ones are associative but not commutative. So which ones we can, if they are in sequence, which ones we can do this one first and then this, and it will be the same. Or, yeah, and subtraction is not neither. Subtraction is not because of the, yeah, let's check it. So if I have -2, -3, -5, and then if I combine those, I don't get the same result, right? So I can't So subtraction is not associative. So the slide was correct. Um, so associative but not commutative. Yeah. Concat is not, because it depends in which order we kind of putting stuff in. So it will be reversed. If we reverse the order, the concatenation will be reversed. Divide is also not, because it will not work. And minus, we already know it's not associative. Right. Okay, we're moving forward. Okay, so now we have to think which ones of the examples are monoids. So we need binary operator, we need identity element. So integer with plus, strings with concatenate, integers with multiplication, Boolean, and Boolean with not. Yeah, so this one is not, because it does not have a binary operator. And then all the other ones are. So all the other ones have an identity element. In this context of this one is an empty string. In the context of this one is 1. In the context of this one is true. And in the context of this one is 0. It's the identity element. And the binary operation is plus, concatenate, multiply, or AND, right? So I think you're getting the intuitions of what they are for and why we sort of care. Okay, so what is the identity element in the set of integers? Okay, super super simple. Zero is the correct answer. Okay, next one. What's the identity element of multiplication? All right. So that one was easier because you get kind of primed. So what is the identity element for the set of strings with concatenate? Again, an easy one. So hopefully you will sort of remember what a semigroup is. It's basically a monoid without the identity element, and monoid is a semigroup with identity element, right? You can recall some of the so empty string is a correct answer. Empty string is a correct answer. There is a space, which is not correct because it has to be an empty string. I don't know why this one is wrong. That looks correct. So empty string. All right. Okay, so what is the identity element in the set of Booleans with the AND operator? Okay. So it's true. So true is the identity element. You might be a little bit surprised, but functions in Haskell are monoids. So what would be the identity element for functions if functions are a monoid? So if we ask tell me about ID, and it's a function which, given an argument, returns that argument. So it's a kind of a trivial function which does nothing. It just gives you what it gets, right? It's an identity element in the monoid of functions because it does not change anything, right? Um, and it is kind of interesting that functions themselves are a monoid because that means we can do certain things with them, right? We can do certain transformations with them, and the semantics will hold. They will kind of maintain the structure. All right, so well, that one was like didn't change anything. Everybody got at least here maxed. So, functor. You already know functor because you've been doing exercises with map. You have been mapping over lists and so on. So in category theory, functor is basically a mapping between two categories. So if I have a list and I map over that list and get another list, I have two categories, which are my two lists, and I'm doing the mapping. And this mapping is a functor, right? So you can think about it as a map. So functor, kind of think about it as a map. Unfortunately, the C++ designer, Bjarne, he thought about kind of a clever way of naming something a functor in C++, and you can read about it, but it's not really a functor. It is not the same concept as we do have it in the category theory and in other programming languages. So C++ is a little bit of an exception. It's like a weird, like he wanted to differentiate functions from something extra, and he called this something extra functor instead of function. But it is a bit of an unfortunate coincidence, right? So functors in C++ are not what functors are. So of course, map works with lists. So a list is a functor. So all lists are functors. And then like the fmap for lists, the fmap is basically implemented just as a map, right? So map in lists is sort of like the fmap in more general sense. But in more general sense, you can have different things that you can map over. And two things that we will map over right now in the lecture is maybe and either, which have nothing to do with lists, but you can also map over them. In Rust, you have result type, and you can map over a result as well. So it's basically a structure, it's a category which you can map over. So we have to talk about effects. This one is a bit difficult topic, and it's a bit confusing, and sometimes the intuitions that we have are a little bit different to a person next to us. So we have to sort of get a little bit, like I will kind of share some of the intuitions, but you have to develop your own in a sense. So this one should be easy. You probably already have that intuition. So Haskell program is one giant function composed of many other functions, right? So it's a kind of a little bit unusual way of thinking about programming, because coming from the imperative paradigm, we have a different intuition. Our intuition is that it is kind of an interactive system. So a program is something that interacts with the outside world, and it's sort of the behavior depends on this interaction, and it's more spread over time. And it is a very useful metaphor. And in there is like a special paradigm that we may not be able to dive into in this course, but we may be able to do it later if you stay for the master's degree. So let me with this. So there is a concept called concurrent sequential processes. So the paradigm is called CSP. And it deals with the complexity of processing if we have multiple concurrently processing things. So if we say we have multiple Haskell processes which take input and produce output, right? But in Haskell, we don't really think about it as interactive anymore. Like we think it's just one giant function which takes input and produces output, and that's it. There is no interaction. But you say, yeah, but you know, a Haskell program can ask a user for a username and then asks for an age and then does something. Like we can feel this interactivity there. So that's true, but it's like on the conceptual level, on like how it is modeled, how it is actually organized, it's not. The interaction which appears to us as interaction is really it's like a ball which contains all the interaction inside that ball. And that ball is like passed in and passed out of that one giant function that is sort of Haskell processor. So the interaction is hidden within that kind of a universe of the ball. Again, as I said, it's kind of strange because it's very abstract to talk about it, and people have different intuitions, and the way I think about it might be different the way you think about it. But the point here is that there is no interaction. All the interaction is contained into a sequence of actions which is contained in a structure. And that structure is initially passed into the program. And when the program finishes, it passed out. And to us, it appears as if there is an interaction. But from Haskell point of view, there isn't. It's just this sort of the world is contained in this sort of a structure, right? Which is different to CSP. In CSP, we don't have that. We don't have the ball. We basically have the interaction and we focus on the interaction. So CSP is a different way of organizing our thinking and organizing the processing. So yes, it is one giant function. And it is just composed of many other functions. And to add more confusion, everything is pure. There is no IO, there is no interaction. And say, no, Mariusz, you're lying. Of course there is IO. I can read from standard input and write to standard output. And it's like, yes, it appears you can, but in fact, it's contained in the IO monad. And all you're doing is you're interacting with the IO monad, and it pretends for you that this is what is happening. But it kind of sequences all the actions inside the IO monad. So interacting with the IO monad is also pure. There is no side effects, like nothing unusual can happen. So it's a little bit confusing, but hopefully we will develop some intuitions. So another question: can you do imperative programming in Haskell? So this is again like an arguably difficult question to ask, and arguably any answer is correct. So as you if you are a purist and if you are very strongly opinionated, then you will say no. And you can argue that no is the correct answer. But first of all, you can make a little bit of kind of arguments that it a little bit depends. And in fact, Haskell allows you to do impure and like unsafe things. So as a programming environment, it does allow you to violate the no answer. So it kind of, it depends is also correct answer. But in a strict sense of the design and how Haskell was originally, if we don't talk about compiler, if we talk about Haskell as an abstract concept, then no is a correct answer. Okay, so one more, same category of questions. Can you have impure functions? So it's very similar to the previous question. If you take it literally, and if you take the design principles and how Haskell actually is designed using the category theories, then the answer is one answer. And then if you take the compiler into equation, and if you say, yeah, but it kind of allows us to violate certain things, then you can say it depends. So the correct answer is no, but also you can sort of make certain provisions that it can be violated. All right, so those are kind of difficult, like they will come over time. You will get the intuitions, and then you will understand a little bit more of the nuance of why Haskell has certain properties. So functor, basically, so fmap takes a normal function and something which is a functor and gives you something which is a functor after transforming what was inside from A to B, right? So in a sense, if you think about it, if I have, so again, if I quit that and if I go GHCI and if I have my list and my list is 1 to, well, 1, 3, 10, and then I say fmap something over it. So like, let's say, multiply by 100 over L. What happens is I have this function, and this is a normal function. It transforms a number into another number, right? This function, multiply by 100. But I have a list, and my list is 1, 3, 10. And I cannot apply this function to the list, right? I cannot do this. This is not gonna work because I have values inside a structure, and I have a function which operates on values directly, right? So I cannot apply this to this, but I can map over. So I can do this. And then I have a new structure which again I can map over, right? So I have a values in a structure and the values in a structure, and I can do transformation. And fmap allows me to do that, right? And if I have just Mariusz, I have a maybe type. And yeah, maybe lower, do we have it? No. Lower, no, I would have to import it. So let's say I have just 100. I just have a number, it's easier. And now I have to multiply it by 100, right? And just 100. Can I do this? Can I apply my function to that value inside a structure? I cannot. But if I say fmap over it, then I can, right? And I will get, again, new value inside the structure. And this is a functor. So ability to do this tells me that this value is a functor because I can map over that value, right? It's a value inside a container. So it allows functions to be applied on the structured value. Works between normal functions and structured value, and does not work between structured function and structured value. So what does that mean? So if I have, let's say I have a list, and I have to plus 2, and I have to multiply by 100. And then I have another list, which says I have 1, 2, 3, right? I cannot combine them together. I cannot say, do those operations on those values. Like I cannot do this. And I cannot even fmap it. Fmap it will not work because like this is not a function from value to value. It's those are functions inside the structure, right? So I cannot do this. But there is a mechanism which allows me to combine them together, and we will learn about it in a moment. So functor allows functions to be applied to structured value, and it works between normal function and structured value, and does not work this way. All right, so 4 more questions. Okay, so we're doing fmap of some sort of f to a list of 10 items. What is the outcome? What can be the outcome? Exactly. So it is always a list of 10 items. It does not depend on f because f has to convert value to value. It always does that thing. So if I have a list with 10 things and I have f which always convert value to value, I have to get a list of 10 items, right? It does not depend on what f is. Whatever f is, I always will get a list of 10 items. If I am applying some function to a value inside a maybe type, what will I get out of this? I will always get a maybe type with a value. My initial value could be a number, which was the case. Let us recall this. So my initial value inside the structure is an int or number, and my f is this, and I'm gonna get maybe number, maybe int, right? But it does not have to be the same type. I can apply show to my value inside the structure, and now I got just string, right? I had just number, now I have just string. So it's a maybe number, here is a maybe string. It's okay, but it will always be a maybe type, right? The enclosure, it will always be a maybe type. And it is the same with lists. If I have a list of where we did the lists. Yeah, so let's do fmap show L. It will always be a list of 10 items. Original list was list of numbers. This one will be list of strings, but it is still a list of 10 things, right? I hope you got that. Okay, so maybe it's a value with some sort of state, and the state means we got the value or we got nothing, right? It's sort of like a pointer. You can think of, if you're coming from C++, it's like I have a pointer to something. It can either have something there or it can be a nil, right? It maybe it's the same. You either have a value inside or you don't. And if you don't, it's just empty. You just get nothing, right? So you don't know why you got nothing, but you just know it's nothing. Same with pointer. If there is a nil or null pointer, you don't know why. Why did I got a null pointer there, right? But you know there is nothing there. So we can do some operations with it, and we can do some very nice error handling and kind of transformations. What is a total function? What do you think? If you read the book, you will know. If you didn't read the book yet, you will not know. So I will tell you. So what is a total function? So if I have a function, yes, function without exceptions. Yeah. So if I have a function and it takes some argument, it will always produce an output, right? No matter what I put in, it will always return me a value, right? So for example, plus is a good total function because for any integer or any number I give it, it will give me a result, right? Division, not so total because of of some problems. So if I have a function from A to B, and for any A, it will always give me a B, then it's a total function. But if there are some exceptions, if there are something is not working, then it's not a total function anymore, right? And we have to deal with it. So for the exceptional cases, we have to deal. For the total function, we don't have to deal with anything because it always works, right? So here we have a question. So those are from Haskell, but I mean, just use the concepts. So is minus a total function? Is plus a total function? Division, multiplication, tail, and head. You have to think, do we have special cases? Do I have to think about special cases? If you have to think about special cases, then it's not a total function. So which ones are not total functions? So division is not, because a special case is division by 0. It's in mathematics, it's undefined. It does not exist, so we cannot divide by 0. So divide is nice, but it has this one exceptional case where we get nothing, or we get not a number, or we get undefined, or we get something unusual, right? Plus and minus are fine. Multiplication is fine. We always get number. Tail and head are not total functions, because if I have an empty list, what is the head of the empty list? What is the head element? There is none, because the list is empty. And then what is the tail? If there is no head, there is kind of a little bit weird to talk about the tail of the empty list, because the tail is what's left over from the list if you remove the head. But if there is no head, it's a bit tricky, right? So those are not total functions. And if you say tail of an empty list, you get an exception. If you say head of the empty list, you get an exception, right? Exceptions are not nice. Exception makes our code complicated. We have to deal with it. As programmers, we have to deal with exceptions. We don't like exceptions. We really love total functions. Total functions are so nice. They always work. We don't have edge cases, and we don't have to deal with them. So if you can organize your work, your concepts, everything into total functions, then you will be great, right? So that's where maybe comes in, because if I have this, and if I say I have a function which converts A to B, but sometimes there is no B, sometimes I cannot do it, and instead I say it converts A to maybe B, then it's a total function again, right? Because it will always return maybe B, always, every single time, even for exceptional cases. It will just return nothing, and I don't need to deal with it. Like the function always returns fine. But if I have A to B and I have exceptional cases, then I have to deal with exceptional cases, because I cannot return. Like if I say divide by 0, then like what should I return? Like, okay. But if I say maybe B and I say divide by 0, I just return nothing, and it works, right? I deal with it later. So we like total functions, and we always want to write total functions. And in Haskell and in many programming languages, if you have a function and it is not total, the compiler will complain to you. It will say, your function does not deal with those extra cases. You probably have seen it already. Like the Haskell is picky. Like it tells you like, oh yeah, you're not kind of, your pattern matching on your function definition is not completed. It's like you missed something. All right, so maybe encapsulates an optional value. It's great for representing some sort of structured value. And for exceptional cases, you just return nothing. So it's really good for dealing, doing processing when something can go wrong, and for error handling. And you have some utility functions. So you can extract the value out of maybe, and you can ask, is there a value, right? So those two functions have to be combined because you can get nothing, right? So if you have nothing, so is this a total function? Is this from just a total function? No, it's not. This function is not total because it will throw an exception if you ask from a maybe type, which is nothing. It will say, but there is nothing. I can't give you the value. It will actually throw an exception, right? Okay. This one is a total function because it will always produce maybe b, no matter what happens here. In an exceptional situation, it will just return nothing, but it will always work. Maybe is a functor. We already know it. You can map over it. You can chain the function applications. You can have a nice composability. And this is exactly what languages like Kotlin or Rust are using. They making certain types functors such that you can use this fancy question mark operator, or you can chain things in a kind of a monoidal way. Again, very simple example. Get a number from a user, which can go wrong because the user can say Mariusz instead of giving you a number. Add 10 to it. That should work. Multiply it by 2. That should work unless the number exceeds our space limits. So maybe the user gave us like a very max integer and we cannot multiply it by 2. We kind of have a overflow and then we convert it to string. So things can go wrong. So at the end, we either get string or we get nothing if something went wrong, right? And composability is a big deal. We do a lot of things to enhance our composability in our own implementations, and especially if we're doing frameworks for other people. Other people usually like being able to compose things. Okay, so then we have either B, and either B is like an extension to maybe, where instead of saying we got nothing, we say, well, we didn't got the actual value, we got something else instead, and that something else can be used as an error, can be used as a describe why we got nil or null, what happened, like what happened that we don't have a value, right? So we either have a value or have state, we have something else. And this either is basically a combination of two things and a structured value or a reason why a structured value is missing. And again, there are some utility functions. Is write a total function? Is it a total function? So it takes an either type and tells you if there is a B. It is a total function because if there is no B, it will just say false, right? So if there is B, it says true. If there is no B, it says false. So is left and is right are total functions. But from left and from right are not total functions. If you say from left and you have either type only with right, it will throw an exception. It will say, yeah, but I don't have a left side. A left side is missing, right? So those are not total functions. Those Boolean functions are total. Are those functions total? Lefts and rights for a list of either types? Those are total functions. They will always return you a list of A's or B's. And if you have lefts and there are only rights, it will basically return an empty list, right? So those two are total. Those two are not. Those are total. You have to get used to it because when you're programming, you have to know if your functions are total or not. And if they are not total, you have to deal with edge cases, right? Because if you're using from left in your code and you didn't like check if you really have the left side, then your program will blow up. You will have an exception. You have to deal with it. So we try to avoid it. We try to avoid using things like, for example, from left and from right. If you're using it in your code, it's a code smell. It means you're doing something wrong. You're not supposed to call those functions. If you're calling from just, if you're calling, where is it? Yeah, if you're calling this, you're also doing something wrong. You're not supposed to call from just. You're supposed to use pattern matching, and you're supposed to use composability such that it is implicit and you can not mishandling it. If you're calling it, it means you have to deal with edge cases, and you probably are gonna have bugs and miss something. So you're not supposed to call it. It is considered a kind of a anti-pattern or a code smell. Like every time you read code which uses it, you have to wonder why a person is using it, like why we have to use it. Okay, so two more questions and we are done. Okay, that one is easy. So in Haskell, this type is called either, and it is used for error handling. In Rust, this type is called result, and it is a tuple of like a value or error, and the name result suggests it's not a generic type. It's something that you use for specific case, like for some sort of error handling, for result handling. In Haskell, it's called either, which suggests you can use it for anything. Like you either have left or right side, you can use it for anything. And it is true, you can use it for anything. You can use it for union-like data structure as well, but that would feel wrong. Because you have the ADTs, you have algebraic data types in Haskell, and that's what you use for union-like data types. You don't misuse either for that purpose, because either has right and left, and the left and right have kind of meaning in the error handling kind of situation. But in your normal domain, what would left and right mean? Instead, you should have a different names. You should define something which has meaningful names for your left and right side, such that it kind of is obvious. So you should use ADTs. All right, two more. Okay, this one is easy. So as you can see on this slide, it is very common. Many programming languages have it. And you know, I was surprised learning about it that I didn't learn it until like I was programming for like 10 years, that there is this concept of either. And like, I really love it. Like, I really like this concept of handling missing values and errors instead of doing all those if statements and if nil or if null kind of bullshit. This is so much nicer. So many programming languages have it built in, and all modern programming languages have it built in. You don't kind of get it yet in some languages. And if you do, it feels a little bit awkward. Like you could define type like this in C++, but it would feel a little bit non-idiomatic in C++, right? But in Rust, it is built in. You have the result and you're supposed to use it. Right, so then we have a final question. We had a little bit of shovel in the, but Johnny is leading the pack. So then we have this applicative functor. An applicative functor is what I told you functor don't have. So functor does not allow you to take a structured function and apply it to a structured value. But applicative functor allows you to do that. So I can have a function inside a structure and apply it to a value in another structure. So let's it is a mouthful, but if you play with GHCI, it feels nice. So if I have just 10, okay, so I have a number, which is a structured value, right? I have a value inside a structure, and my value is 10, and the structure is maybe number. And now I can fmap, so I can fmap show to it, right? So I can say, okay, call show, which takes a value and gives me a value on top of the structured value, and it will give me just 10 as a string, right? But if I have just show, I cannot map it like this. That's not gonna work, right? And like, how can I apply show to my A and show is inside a structure as well, right? And the way to do it is with the applicative. This is exactly what the applicative functor is. It basically takes a function from A to B, which is inside a structure, applies it into a value, which is A, inside a structure, F, and gives you a new value, B, inside the same structure. So F is the same. It's a maybe something in our case, in our example, but now it will work, right? So why it is useful? Well, it is useful because it works even if one of the sides is nothing, right? And I don't have to deal with special cases. So if I'm composing stuff and I have processing and values and I'm applying values to processing and so on, and like on my unhappy path, something went wrong, and one of the things is wrong, I can shortcut, I can go to unhappy path, right? So again, this symbol, this application of structured function to a structured value allows me to compose things in a very robust and very convenient way. So instead of from just, right, you should not supposed to call this. You should use this, right? So if I say I have to call show on top of something that can be nothing, no problem. I don't, like, if my A is nothing, I can still fmap. I can still fmap show on nothing, and there is no problem. There is no exception. There is no error handling or anything. It just goes into an unhappy path, right? I don't have to check, oh, from just, do I have a value? If I do this. If I don't, do this. No, it's like I'm trying to deal with the happy and unhappy path in a very consistent and very easy way for myself. All right. So final question. Yeah, that's the hardest question so far, but I already showed you the answer, so it should be super easy. So you have plus 10 in a structured way, and you have just 3 in a structured way, and how can you apply this just plus 10 to just 3? You use the apply operator, and then it just magically works. So nobody got the syntax right. This is correct. Yeah, this is correct. It's just that this plus is confusing. You have to put that into extra brackets. You have to put that. You don't need the outer bracket, but you need the bracket around plus 10. But it is correct. This one is fine. So one extra trick, again, for those of you who are a little bit on the adventurous side, I can show you that I can do show. And I can do plus 10. To a set of numbers, 1, 2, using the applicative functor all in one go, right? I can apply 2 functions to 2 values, so I have to do 4 calls, right? I actually have to do 4 calls. I have to do show 1, show 2 to get 2 strings, and plus 10 to 1, which to get 11, and plus 10 to 2 to get 12. So I'm doing 4 calls just with one, yeah, what you don't like. All right, let's cheat. Let's do, yeah, so, okay, so the reason why it didn't work is what? The reason why it didn't work is because show gives me a value which is a string, and plus 10 gives me a value which is a number. And I cannot have a list which has numbers and strings in the same list. Lists in Haskell are strictly typed, so I have to have both functions doing something with numbers, right? So I can do this, but I cannot do show and number, right? And that gives me those 4 results. So I'm kind of doing 4 function calls, and I'm getting 4 results, and in a structured value, in a list, right? All right, so that's it. Let's have a break. I have exhausted the slide deck. Took a bit longer than I thought, but I got through it, and I think you got a little bit more intuitions about structured values and non-structured values. And you were using it like with C++ and with other programming languages. You were using it because you usually have a pointer to something, and it could be nil, or you have an object or a struct that you kind of manipulating from outside, or in other ways. Like we have this sort of concept of structured value and state in other programming languages, but it is not as tightly coupled. In functional programming, it's very tightly coupled. And in the future lecture, we will talk a little bit about the state and how to manage state in Haskell. And this will come really handy, this sort of metaphors about values in boxes and structures that we manipulate, both on the processing side and on the value side. The processing side is new. This ability for us to manipulate the processing is a bit new, because in imperative programming, we say, do this to those values, then do this to those values, and so on. So we kind of manipulating the values, but the processing is very rigid. It's sort of the way it is. We don't really think too much about it, right? But here we can pass processing to other functions and do meta processing often. I mean, you have it like if you're using templates. If you're doing a little bit more like template-oriented programming, you're touching on that. But in functional programming, we using it almost everywhere. It's almost everywhere generic programming and sort of template-like programming. So it's a little bit more complicated to get your head around that the processing can be organized into these structures, into the kind of ways to deal with errors and to deal with complex processing. Anyway, I will shut up. So let's have a break. Let's have a 10 minutes break. And I will post the task 9 for you to start working on in groups. And you basically have to read code, play some snake games, and think about the code. You don't have to code anything. And for the task 9, we're not using AI. We're just looking at the code and like thinking. So I will post it now, and you can start after the break. For online people, I'm gonna stop recording, and you do this at home. So you check task 9, do as much as you can now in the class, and then you can ask me questions. I'll be around, and TAs are around as well. And then there is one more week to work on it at home.